Hello everyone, welcome to today's webinar. We'll begin in 1 minute, right on time. Chat then. Hello everyone, welcome to today's webinar. We're going to get started right on time straight away. So today Adam will be presenting on CLT design for a residential mass timber building. All right, so before we get started, I'm just going to take us through the agenda for today. One moment. Let us know if there are any issues with our slides throughout and we'll be sure to fix it. So before we get started, I'll introduce myself properly in a moment. I'll take you through some housekeeping and then our latest releases that we've just had and we're about to have. And then Adam will get onto the design example. So to introduce myself, I'm Corey Jones. I'm the Customer Success Manager here at CLT Toolbox. I also happen to be Adam's wife. I'll take you through the housekeeping in a moment, but I just wanted to mention that this is Marco and Philip, our product management team in Serbia. Our co-founder Ringo is actually on a plane coming back from visiting them as we speak. So I think they all had a wonderful time together. So very jealous and can't wait to hear all about it. So to get into it, some housekeeping. So you'll see there's the question icon button at the bottom of your screen. So if you pop questions throughout the webinar in there, Adam will be sure to answer all the questions at the end. And there's also a separate chat feature button to the left of that. If you want to say hello, say hi, have a chat throughout, go ahead and use that feature as well. Just to reiterate that we actually this is recorded. So we do have our webinar recordings on our community forum and they also go up on YouTube, but we also, if you're time poor, we cut our webinars down to small tutorials specific to each topic. So you can kind of find 4 to 8 minute videos on YouTube as well if you want to look at a topic more specific. Okay, so just wanted to speak to our latest release. That was release 2.1.5, the brackets and connections release. So what happened in that release, we had connection module, bracket modules with Eurotech and Sigga. We had the shear reinforcement calculator, connection details, slab to wall screw connection, wall to wall screw connection, and we had some updates to some features, including duplicate projects was enabled and screw ordering fix. Just wanted to make mention that we do releases of this magnitude every 2 to 3 weeks. So the software is improving at a very rapid pace, which is exciting. This is a release that we're hoping to release this Friday coming up. This is release 2.1.6 shear wall update, floor penetration and studs. So there'll be new member calculators, both stud design and floor penetration. There'll be a major update to the shear wall calculator and CLT beam calculator. And as far as features, we've got a big improvement to the PDF printing, so that's exciting. We also always want to thank our partners. This platform wouldn't exist without our partners. They're absolutely incredible to work with, and we thank them so much. And we're really excited to be constantly onboarding new partners, and we're really excited to have them on the platform. So stay tuned. There'll be further partner releases in the coming months, which is exciting news. And before we get started, I just wanted to make mention that myself, Adam and Ringo will be at the WCTE next week, which is very exciting in Brisbane. We're flying up this weekend, and we'll also be hosting the welcome drinks. So come say hi to us. That's on the Sunday night as things kick off. Come say hi, come have a beer, come have a chat. We're really excited to be there, and we're really excited to see everyone. So without further ado, Adam's going to get into the CLT design for a residential mass timber building. Thank you, Adam.
Thank you very much, Corey, and good morning, everybody, and thank you for joining us today. So I'll take the screen and we'll take it from here. Okay, so as part of today's presentation, we're going to be looking at a residential apartment building or a hotel building. And in terms of the presentation, we'll be looking at some context across fire and acoustics. We'll be doing some CLT wall design and eccentricities, and we'll be doing a CLT wall fire design, a shear wall update, brackets design, a connection detail, and compression perp to grain, and also the floor penetration sneak peek. So come to think of it, there's a lot to actually get through. So some of our webinars, we go deep into one or two calculators. Today, we will be covering quite a bit of ground as well. So hopefully that works for everyone as well. So it's always good to start these webinars by taking a step back and looking at the building type that we're covering today and some of the different examples that are out there. So Forte, I think that was 2012, maybe, that went up, and that was by Lend-Lease. That was the first honeycomb type structure where you got CLT walls and floors, but you can see the CLT walls in both directions working as a shear walls to get a really stiff building and a really efficient building type that can actually be installed really quickly. And there's other building types like that have happened since then. So in Auckland City Mission, I think that's a 10-story building as well by XLAM. That was done in a seismic zone, so just showing what can be done in a seismic region with these building types as well. And then also Adelaide Oval Hotel, which is a bit more recent as well, and another project by XLAM. So before we get into the structural design, it's always good to just touch on the multidisciplinary aspects. There's a lot of different things we could look at, including DFMA, durability, sustainability, but I think it's always fire and sound that comes specific and probably touches the structural engineer the most. So fire design point of view, we did do a webinar last month which covered this in detail, but very simply thinking, or the very simplistic version of it, when timber is exposed to fire, you do have a charring mechanism that reduces the capacity of the wall panel for the duration of the FRL. So that's one aspect that needs to be considered from the structural engineer, and we'll be covering that today with the fire design for a wall, but also sound as well. So understanding how sound transfers, you do have a flanking mechanism that actually attaches potentially to a wall and then attaches to the floor, and through that can actually transfer to the adjacent apartment. So you've got impact sound and airborne sound as well. So when you're thinking about the junctions of walls, so say between apartment buildings or hotels, this can be quite critical. So, and there's different ways to skin the cat. And this is based on as well what's been preferable from the client or the architect. So in this case, you might have a standard solution. Excuse me. You can see here you do have plasterboard, no exposed timber, and quite a fire protected system. It looks almost like a DTS solution in this instance. But on the other hand, you could have an exposed soffit. So if you wanted to expose the ceilings, that's one option. But then you have impacts on the acoustics and how you achieve the acoustic system. If you look at that from a flanking perspective, I mean, there's quite an obvious flanking path. So the acoustic consultant might not be so happy with that. Another option is you could perhaps expose one side of a wall. With that, you do have an exposed fuel load in this case. You do have a benefit from an architectural point of view. And you might use isolated rubber pads, and there's different suppliers who can supply that sort of product to help deal with the flanking issue. Or you could have two adjacent walls like this, and that might be better from having a discontinuous space in between to improve acoustics. But again, there's different ways to skin the cat, and all of them, as you solve for one discipline, you might have implications on the other disciplines and cost impacts. So again, collaborative approaches, and also asking, say, the supplier about what their standard solutions are, because if it's a standard solution, then you're most likely going to be benefit from experience. So from here, we're going to look at now the structural design of the residential mass timber building. So you can see for this building type, it's so Marco, our European product manager, put this together. So there is a pretty small floor plate you can see here. So this is in centimeters, these grids. and then you've got A through to E. So pretty short sort of floor plate, and it's spanning 15 to 20 meters and a 16-meter height. So for this, we're going to start with a wall design. So if we're starting on the external wall within the building, we're going to begin by looking at from a non-fire perspective, and then we're going to design this from a fire point of view. So for just 3 levels plus roof and a pretty small tributary breadth, you do end up with a load of, say, 21 kilonewtons, 21 kilonewtons dead, 12 kilonewtons live, 4 kilonewtons snow. And for this case, we're going to just make an outer plane wind load. And then where that gets quite interesting is from a fire perspective, how you deal with the bending moments when there's eccentricities and a lot of complexity in that scenario. So when you're designing walls, there's typically 2 types of framing. You've got platform framing, where you're essentially just putting the floor underneath and stacking the walls on top of it. There are contexts where that might make sense. It is the most common type of construction. It's very easy and straightforward. The other approach is using a double height wall, for example, and with that, you've got a balloon framing in this instance. So the floor will budge up and sit upon the balloon framing here, and the wall would run all the way through. So from a perpendicular grain crushing perspective, there's nothing to check here. You've got maybe an additional bending moment with an eccentricity from this floor reaction, the differences from an installation perspective, and so forth. But we're going to be looking at a platform framing point of view, and that being most common. The second thing to consider when we do our wall design is the eccentricities. So this does impact the design capacities quite significantly, and there's different methods of dealing with eccentricities from around the world that we're going to cover in our wall calculator. So a few different definitions. So firstly, you've got geometric imperfections. So this is where you have deviations that might happen within the panel itself. So the construction tolerances actually should be a separate input here. But when you actually have the panel itself, you might have knots, you might have different material stiffnesses and strengths. And that with that, you're not going to have a perfectly aligned panel essentially. And with that, you do have an induced eccentricity. You got the actual load eccentric above. That might be where the construction tolerances come in. So you've actually don't have a perfectly aligned wall sitting on top of each other. You might have an outer plane deflection from a wind load causing a shift of or a deflection and a P delta effect. You'll have a neutral axis shift. So imagine if you've got a fire on one side moving where the neutral axis is, but the load above, it's where, say it's at the centroid, and because of that, you'll have a bending moment induced, and then a second order eccentricity as well. So with that all said, we're going to fire up CLT toolbox. All right, so with this, we're going to be doing what's in the app now, and then some of the back calculators are going to be on a special link, which is going to be released on Friday, essentially. So if you're new to our platform, you can see here you got member calculators. You can see in Alpha, we've got the stud design, which is about to be launched, and also the floor penetration. And you got connection design as well. And quite rapidly, we're basically finally getting to the majority of the roadmap of the initial, front page UIs that we've had. To design a wall, you click CLT Wall, and with this, you can choose CLT Wall Design or Fire Design, and then save it to a project. Alternatively, you've got your different projects here. So if you've got your own projects, shared projects, or a company project, if you've got an enterprise panel, or you got your recent projects here. So I'm going to open up that one I created earlier, so on webinar 5, just to have all the inputs ready to go. So from the project management page, you can have discussions. You can add other colleagues to share the project with them as well. All right, so let's fire up the wall design. So we're going to begin with a non-fire case, and then you'll see when we design for fire, fire does typically govern the design if it is exposed, as you'd imagine. So a few different inputs here. So you can see on the right-hand side here, as we're designing, we can see the summary and all the different checks. From a top view, you can see our wall that we've got designed, but also a section view here where you've got an eccentricity, the height of the wall, and an outer plane wind loading in this case here as well. You can change your supplier as well. So if we're in Timberlink, for example, you can always choose your layup and so forth. All right, moving down, we've got the design code next. So I think it's important sometimes to check at least the Eurocode as well as AS1720 design methods. You can see here Eurocode, for example, has a slenderness ratio check. So I want you to keep an eye on that as we go to AS1720. So for Eurocode, that's what's governing the design right now, as you can see. But as you get to AS1720, that slenderness check is gone. So, and again, you're just left with pure, combined bending and axial forces as well. So as you swap between methods, you'll get a feel for what's conservative and what method you want to choose, and also to have the apples with apples comparison if you're doing a local supplier with a local code compared to, say, European supplier and European code. But let's keep it for AS1720 for the moment for the rest of the design. Next, you've got your analytical methods. So we've got 3 different methods in here. And for those new to the platform, you've got this more information to just always be learning about all of the inputs. Intermediate restraint we don't have, but if we did, you'd say yes, and you'd have a restraint at half distance. The height of the wall, 3 meters. And in terms of framing, remember we had platform or balloon framing. And if we chose balloon framing, it'll let you choose assumptions to have for the balloon beam inputs. Let's keep it as platform. For loading data, we've got a dead, live, wind and snow load in this case. So let's just say if we're in a snow region, and it'll be based on an AS1170 loads with the default load combinations that we've got on the platform. Load combination factors, self-weight and considered for the wall, and then you input the load. So these are the loads that we already had and pre-configured before. Then finally, the lateral load from wind is the outer plane load. So if you turn that off, the outer plane load's taken away, but of course, we're going to have the lateral load from the wind. Next, you've got the eccentricity. So this is where we do have multiple methods built in because we have we've launched a beta in USA, in Canada, and Europe. So that means you can actually compare and look at all the different assumptions from around the world. And it does deal with the geometric imperfections and outer plane loading and P delta in slightly different ways. And at least when you choose one, you can at least click on the eccentricity and inspect the calculations. So right now we're on revise Eurocode. And with this, we do let you choose and put your own manual input for eccentricities above, but then in addition, it's calculated specifically to Eurocode. Finally, you got your design code, so your normal K factors, and we can put that in as well with additional inputs here. So if you require your K12 calculation, you can manually input yourself as well with other inputs here to learn about. All right, so with that said, we've now got our output summary. So if you look at our calculations, you can look at this in detail. Panel properties, we've done that a lot in almost every webinar, I'd say. For loading combinations, you can see how these are calculated. So all of these are first calculated separately, then are combined for our default load combinations. So the actual load above and lateral load as well, and then combined together to get the load combinations which are used for design. And as you untick boxes, the load combinations will change. It is worth mentioning we do have a manual load combination as well, so you can override that. Next, you've got your eccentricity. So you can look at the calculations here. So this is your manual input version directly above. But in addition, you have the calculated eccentricity here. So with the draft Eurocode, you have an equivalent bow imperfection, which has an additional eccentricity, plus the outer plane wind loading, because we do have that wind load from the external wall as well, creating an additional eccentricity here. Next, for analysis, you bring this all together. Again, you got the axial load from above, and then you got the design axial loads with the loads at the level of the actual floor, because the load above is different to, say, for example, the self-weight and so forth. You got the bending actions, which is the eccentricity multiplied by the design axial load to get the actual moment. And then you got the moment due to out of plane wind pressure. So again, that's calculated slightly differently. And then you actually design the nonlinear moment as according to the draft new Eurocode. And then you bring it together, you've got your design moments. And we've got diagrams here so you can follow along. So for example, for a case where it includes everything, including the outer plane wind loading, you can see the bending moment that we reach is about 5 kilonewton meters as we go up the wall as well. All right, so that's the analysis of the wall. So there's a fair bit going on. And then finally, we've got the design code. So I'll design here to AS1720, but if you change to Eurocode, you could follow along as well. The first thing to do is calculate the K12 for bending. So your K12 bending It's a function of a material constant, which is a ratio of your stiffness or your Young's modulus divided by the bending strength multiplied by the temporary action design effect. So this is a moving part depending on the load combination, but also the lamellar buildup. So for some suppliers, they don't have homogeneous layups, meaning you have to break this out layer by layer. Next, you can calculate the slenderness coefficient. And then from that point, you can then calculate your K12 factors. So you can see here with our K12 calculations here, we are 1 for every single loading combination in this instance. Because you have an outer plane bending, but in addition to a pure axial load, you do have to calculate your K12 different for bending and compression. Hence, we've got a K12 calculation now for compression. Pretty similar, but different because right now it's pure axial capacity as well. And in this case, you can see here, you can see here the K12 is 0.42, whereas previously, essentially, because it's restrained, it's a wall, it's 1. So moving through, you can see here we've got individual lamellas broken out here for the different strengths. That's in the case if you have a non-homogeneous layup. Then finally, you do your axial design. So lamella by lamella, we do the design here to work out the capacity, and then the different capacity based on the different load combinations and K1 load duration factors. And moving through, then you've got your capacity. So that's for your axial. Next is your bending capacity. Again, this is going to be a function of the eccentricities and the bending moment that we've already designed. And again, you get to the utilization here. Then finally, you have the combined actions effect. So that's for AS 1720 using those methods of design. But again, as a user, you might just check Eurocode, get a feel for it, and see if there's a different check that's not included. In this instance, for example, I won't go through it in detail, but you do have a slenderness check of a limit of 150, and that's 76. Hence, it's like your slenderness could be the governing factor if it was a European method. Hence, you might be more comfortable not going with such a slender wall, for example, or not. All right, so at the end, you'd save, and then you can, of course, print the design and everything like that. So next, we're going to go back to our apartment building. We're going to look at things from a fire perspective. At this stage, we have separated our fire calculators from the ambient calculators. Later in the year, they will be combined. But having said that, I think it's better to have them separated at this stage because they're complex enough as it is, and to not be a black box. It's good for every engineer to lean in and actually get a deep understanding of, say, fire by itself. So what you're looking at here is the default inputs I had before. So firstly, you've got your layup. You can see for a 90-minute R, which is a 90-minute FRL, based on a right-hand side fire, you can see protection here. So thickness as it burns through with minutes, it steps there, and then it burns through. And after the zero strength layer, we end up with a 60 mil design thickness left, and we've got a T design with 110 mil layers. So for this instance, we did do a webinar last month, and I recommend going in detail. We go into the different charring mechanisms. We compare the Austrian National Annex to the new Eurocode to AS 1170 Part 4 and so forth. All right, so that's our design lamella based on the input. So next we're going to look at the check. So here you got the Austrian National Annex, the draft Eurocode as well, or a standard fire test. If it's a standard fire test, you can manually input protection times and so forth. For our fire data, we've got a 90-minute FRL. The nomenclature sometimes is default European in some instances, like it is here, but you can see here it does refer to the fire resistance level, and you've got different inputs here and different rough numbers based on the checks, but of course, go to the building code to get the specific FRL inputs. For char rates, you can do your CLT supplier. So if we're doing local suppliers, always, I reckon, get it from your suppliers if we haven't wired it in yet. But just to manage that, we're just going to keep it at 0.7 millimeters, not saying that's the supplier's chosen char rate, but check with them. For sides exposed, we do have one side exposed right now, which is the right face, but you could do both sides if we wanted. Next, you've got your char rate, your notional char rate. And again, you can do the more information to learn a little bit about these informations, and you can learn about the different phases of the charring methods available and so forth. For protection, we've got 2 layers of gypsum plasterboard, but we could go, say, unprotected walls, and you can see what happens in that instance, right? So, but for us, let's make it protected, and it is working dynamically. So these are quite powerful fire design calculators to use. If we did change to the new Eurocode, you're going to see a totally different assumptions when it comes to the zero strength layer, and we've got a more conservative design when we do new Eurocode. And you can see here right now we're failing based on slenderness in this instance. Analysis data. So these are inputs I predefined before. So 3 meters, we're still platform framing. Loading data, 21 and 12. Eccentricities. Let's just do manual input for the moment. And then you got your design data. So with this, you can go through the details again. It's not a black box, so you can see all the assumptions on protection, the different phases on the different char rates, because you do have different char rates when you've got a protected or an unprotected, and also protection times as well based on each lamella. And then following getting your charring, you've got a reduced section then, which you can then recalculate your panel properties for new loading combinations. Then you can do, well, the eccentricity in this instance, but if we did say revised Eurocode, you can see the calculations update and it is modular. And then you can do your analysis. So for an analysis, moving through for the new Eurocode, you can see the design in detail and you can see the bending moment and the actual load that's taken for the analysis. Then finally, a design of the wall. So with that said, let's just go back to, well, you know, you can see here we're failing right now for the wall in both instances, and you can look at it in detail. So with that, Eurocode does do a slightly different design flow compared to AS 1720 Part 4. And again, at the end, you can see the combined bending stress lamella by lamella as well for the unsymmetrical section. So that could be handy as well. I am going through it quite fast because we are covering a lot of stuff today. But you can see right now, based on the inputs, you know, we might need a thicker panel. We got it working. You could obviously go more efficient with you spending more time. But you can see here, based on all those inputs, we were governed by fire in that instance. We might need a thicker panel for a 90-minute FRL in that instance. All right, so next we're going to look at a shear wall design. So this was a bit of the focus of today's webinar. So we're going to spend a little bit more time on this one, and this will be basically in the app in the next 7 days with some pretty key updates. So let's go through it. So for our shear wall design, so there's the analysis part can be done outside of CLT Toolbox. Sometimes there is a pretty quick hand calculation method to work it out based on trib width and based on your wind loading. So that's what we're going to do in this instance. So say a 5 meter trib width to actually work out the level by level lateral load on our shear wall. So when it comes to shear wall design, there is a bunch of different checks. So you got the panel itself, the tensile strength, particularly around the area of the tension zone with an assumption around that. You got your compressive strength. Buckling check is in Eurocode. You got 3 failure mechanisms for shear. So that's 4, 5, and 6. Then you got your connection design, so your hold downs, and then your angle bracket design as well. All of these can be done in CLT Toolbox right now, which I'll take you through. So one of the most interesting assumptions is what you put in around your connection transfer mechanism. With this, we do have 5 different mechanisms that you can choose from. So the first method, it does have a rigid body rotation, which is a balance of the internal force. So you can see tension and compression balanced here. That has different impacts on your compression zone and your tension zone. Or you've got a simplified rectangular stress block, which accounts for frictional resistance here. And then again, you have a compression and tension zone with slightly different assumptions. Method 3 here is pretty similar, but with this assumption, you do have a stiff foundation, which impacts the overall calculation. So all of these are done in detail in the app, which you can go into. Method 4, excuse me, this assumes a totally rigid body, and with that, you have a higher tension zone. And then again, that might have a different impact on your hold down design. And method 5, assumes a triangular tensile distribution, as you can see here with the shorter compression zone. So for us, we have a different lateral load as you go vertically up the building. This accumulates a shear force, but it also accumulates the bending moment that's taken onto the bottom shear wall, which is then designed as angle brackets, hold downs and angle brackets through to the transfer level below. So let's fire up the shear wall calculator. All right, so for the shear wall, I'm going to, let's start from the start. I'm currently on the dev version about what's about to get released to the app. So you can see the floor penetration, which I'll show you soon as well, will also get released to the app. So let's with this go shear wall new, and I might just need to flick back and forth a little bit because I won't remember the inputs off the top of my head. All right, so firstly, you've got the shear wall calculator. So you can see here, firstly, input your supplier load. So let's just say if we went with a XL5 190 wall panel, what you're looking at here is the front view. So you can see the bending moment assumed, the gravity load, but also the in-plane lateral load as well for a 3 meter height by a 3 meter wall. And then you got both views in both directions as well to cover. So we're going to start inputting some of our assumptions. So firstly, input the lamellar widths. That can be found out in the supplier's design guides. Right now we don't have them in the database because some suppliers do vary that, and some things we like users to have a manual input to actually, dive a bit deeper and be deliberate about what they're inputting. In any case, you can see here the dynamic image updates based on this. For our geometric data, we're going to have a 3 by 4 meter wall for our shear wall at the bottom floor, inputting the factorized load. So gravity, forgive me for not remembering off the top of my head here, but 450, 40, 147, 450, 40, and 147. I believe that was right. All right, so you can see our image of our analysis from the single shear wall being updated in real time. Next, you got your design methodology. So if you do have A1720, that just uses your local K factors if you've got local timbers, but you do have in-plane shear verification methods, either ProHoltz or FP Innovations built in as well. And as you change the assumptions, you can see what the impacts are of each. We have a new feature called missing material properties. This is where we don't have the data from the supply chain as well. So sometimes it's not clearly written in design guides. In that instance, we leave it again for the user to input it. And that's, again, to be more deliberate about what they're inputting, but also for the suppliers to be comfortable to share properties. And sometimes there might be missing material properties in general, but these are relevant to the in-plane shear mechanism value. When we actually do the new update, we'll have more information to educate you on this. But based on the ProHoltz method, for example, you'll find assumptions based on C24 there, which is a different species to, say, radiata pine. Next, you've got your wall connection mechanisms. So I went through all 5 before, and you've got the more information drop down. So here you can choose what assumption that you want to go with. And as you change the method, you can see the assumptions here, all the different inputs do update, and some extra notes around this. And if you looked at the calculations in general, you would have different options available. So, but let's just go with the balance for the moment. For the different inputs, so you've got the edge distance of, say, the bracket. You've got connection provisions of both sides. So let's just say we've got a total of 8 connectors. That's including the hold downs, lateral deformation limit. Based on the inputs, you can see the hold down of 100 kilonewtons is working. 80 it's not. 90 it is. But again, if you change to your mechanism right now, we're failing at 137% for method 2. And as you'd imagine, let it load. Whoops. This is currently on dev, not on app. So hence it's late stage review. So that might, I might just have to refresh. anyway, it's still working. It's just the more information's when it goes to app, we won't have that problem. But yeah, let's just keep it as mechanism 1. But you can see as you change the assumptions, you connect the capacity for your hold down update. So if we assumed that connection transfer mechanism, all of a sudden we need closer to 125 kilonewtons. So, and that again impacts the costs of the project a lot, right? So it's good to go into detail there. You got your angle bracket capacity, so AB angle bracket capacity working at 37%. So we don't need as much there as you can imagine. You can reduce the number of connectors here if you want to get to a more efficient design as well. Lateral deformation limits, hold down stiffnesses. We will input the brackets from the suppliers automatically in the shear wall in the coming months, but right now they are separate. So, and then finally the tension wall strip width. So that does impact the tension strip as well. So you can see here the tension failure and what is the assumption here. And we've got some additional support in there for that design. So at least you can consciously know what are the assumptions to do the check. You got connection modeling. So you can see here we're method 2. So you can see here how the tension was greater than the balance load as you'd expect, but also in detail on how the assumptions are done. Connector capacity. This might be interoperable with the brackets, which I'm about to show you. Next, you got your member design. So the tensile check based on the net tension zone of the tension strip that's been assumed here. Again, we've got some information, educational information as you go. Compression strength. And then you've got your in-plane shear failure mechanism. So we're up to 1, 2, check 3, check 4, which is mechanism 2 for in-plane shear. So for the torsional error loading information, we got that of the torsional section of the glue joints here, and then finally shearing off of the plate entirely. So with all that, they're all the different strength checks. Before that, we did the connection check, and then you got your lateral deformation check based on the inputs. You do also have your overall stiffness of the shear wall as well. That's calculated. So that's in detail. If you were, for example, to choose again just for checking, if you go to Eurocode, you do have a new buckling check. So even if you are designing a local species, you might, or a local supplier, you might again go into detail to understand this. If you wanted to learn about different options, so right now we've done Pro-Holts, but if you did say, for example, go to FP Innovations, you look at it in detail, how the bending deformation, shear deformation is done in detail. So I think the further you play with our calculators, the more happy you'll be with the layers of depth of world research, basically, to help you perform a design at the end of the day. Because we don't have a local design standard yet, it does require to performance solution and engineering judgment at the end of the day. At the end, you can always print, save and print. I haven't showed you a print PDF report at this stage, but I'll just show you right now. As I said, we're in dev, not app right now, so it shouldn't be a problem. Just give it a few moments. So for the shear wall, you can see it's done in detail. We've got a detailed PDF, but in the coming months, we'll also have a one-page PDF is where we don't have all the detail. But if you're sending it to a certifier, something like a shear wall, it might be worth them, knowing it in detail as well. All right, so next we're going to do the brackets. So these are new calculators as well. We're going to go now to app because this is currently in the app. So go back to our apartment. For our calculations, we're going to go to our bracket calculators. So this is also on the front page as well in steel connectors, in the steel connectors category. All right, so let it load. This is also a recent feature where we let it load a little bit differently. So what you're looking at here is a bracket. You got a 3D imagery and a 2D imagery of the specific bracket that's been selected. You got your design codes again. So Eurocode or A1720. You got your densities of the timber, which is an input works dynamically with the databases that we've collected. So right now we have Siga and Eurotech. Rothelbus are going to be in here very soon, and a few other suppliers who are in our screws are looking to now integrate into these calculators as well. In the categories, you got hold downs, angle brackets, shear plates, and tension straps. And then you've got all of the products within the family. And then once you choose the family, you got the different fixing types as well. So this is actually there's a lot of complexity here, and there's huge databases in here to make it all quite easy, because some of these assumptions change the different assumptions that are available on each. And as you change each, again, you've got the dynamic imagery that updates and what forces does it actually resist. So for example, for this hold down, it looks like that. But if you change the hold down, you've only got one force that resists the load. So quite quickly, you should be able to, get a feel for the different calculations. But for us, let's just go Eurotech hold down high load, which is their highest capacity connectors. Let's just go at the high end of it. And it looks something like this, and then we can start inputting our loads. So for the loading data, I think we had about 120 kilonewtons by memory. And then you got design data. So as you're doing it, you can see the check here. We're okay for the design check, 120 kilonewtons. So just working. So it's at the high end of what's available from the Eurotech range, for example. So you can say here and get to a really efficient design. And again, as you change your assumptions on the shear wall connection transfer mechanism, that's going to totally change your bracket design here. And again, trying to find that cost efficiency, but also at high performance. So you're not unnecessarily adding costs to the design. For bracket design, this does work dynamically with their codes as well. So you can see the checks again in detail. So it's pretty basic checks, but a lot of it is the intelligence on the database handling in this case. So with that, we've designed a Eurotech bracket. If you were to change for an angle bracket, let's just go, you've got your different angle brackets with, say, screws. You got the dimensions of the specific product here. You got just a dynamic imagery there. And again, you can change the screws, and there's different patterns here. And then again, this all changes based on the system as well. And based on what we've chosen, we're working quite easily. So we could either reduce the number of brackets on the previous shear wall calculator, or we can change the system here, essentially. But again, that'll be much better when we integrate that dynamically into the shear wall calculator. All right, moving through. So we're making some good pace here. Next, we're going to look at compression perp to grain. So you can imagine crushing of one of these external walls as the load goes up the building, because we are doing platform framing, as we mentioned at the start. So one of the important things to note, particularly in our local context, is you're actually going to be quite careful around this. And even in using our app, it does, if things get me nervous sometimes, it's like we probably just need to double down on some of these things a lot more. And that is like A1720 uses different tests to essentially work out what the capacity is. And you can't basically use F-P, which is your bearing strength perp to grain compressive strength, with the FC90 and Eurocode. They are quite different checks. And sometimes some engineers may use them interoperably, and you're not on the conservative side if you use, say, F-P of 10 MPa for, say, an MGP10 product. So we've done 2 blogs on this quite recently, so I recommend looking at these in detail where we actually cover it as well. With that said, we're going to now fire up the compression perp to grain check. So for us, we're a 40 kilonewtons per meter load for this external wall. So for our design, we're going to stay in app, and we're going to go the compression perp to grain check. Whoops, I think this is the GLT compression. Just click the wrong one. Just give us a moment. Slab to wall, that's a connection detail. Yeah, compression continuous load. On the front containers of the calculators and connections, you'll be able to see that in detail. All right, let it load. So you can see here what we're looking at is a dynamic view here. So you've got right now you've got your layup of the actual floor itself. So if we could have say for our wall, our floors, say we've got a 5-layer 170 panel configured top. Let's just say we've got a 170 panel for our walls as well. You got the option for a different underneath load or above load as well. And you can see how the load transfers in between this zone here. So it fans out at this load here. But you can go edge parallel to grain, like you can see here, like in our scenario, we're right on the edge. So you're only getting that benefit on one side of the input. So let's just pop these back in again. So we've got 170 above in a 170 floor. So for design methodologies, we do have both options available. You've got your loading data as well, which I think we had 40 kilonewtons per meter. Out of my, I guess, nerves, even though some suppliers do publish F-P90, I've quite recently on some of it, I'll put it as 0 just for the user to, again, intentionally put in the capacities here. And with that, you can put in 10 MPa, but say in the Eurocode, it's 2.5 MPa as per ProHoltz for C24 species, but you can input it layer by layer. So that's based on Eurocode, but for AS1720, we do have the option for just a check as per AS1720, which again is probably currently done quite a bit, but with an F-P of 10 MPa. But I think, again, being able to interoperably change design codes as well, you'll be able to really quickly get an intuition of it. Then you got your net X cross-section check. So you can see here, we are working quite easily based on the assumptions at roughly 5%. But if we went to Eurocode, it's not working as well. It's working quite easily, but not as conservative, I guess. So that design is done pretty quick. And we are working in that scenario and not getting pushed too hard just because it's not taking much load in that instance. For a 6-story building, if you've an internal wall for a 6-story building, like I'd say by intuition, this wall here might start governing at 7 stories for compression perp to grain, and you might need to start doing reinforcement. But in this instance, we've just got an external wall, 3 or 4 stories, not much load. All right, we're going to do 2 more calculators quite quickly. This is a new connection detail. It was recently released. It's a floor-to-wall connection detail. With this, we're going to do the same panels that we did earlier. Sorry if I've been interoperably changing some of these panels in this webinar. And we're going to design screws as well for this connection detail. So one of the things, remember to always save your calculators as well. Moving back here, we're going to go to our connection detail. So we've got our slab to wall. You can add calculators from this view, or you can add calculators from the front view as well. So for our loading, what did we have? We had 25 kilonewtons per meter for the diaphragm reaction into the wall. Alrighty, so you can see here, we've got a top view right now. We've got, what you're looking at is a top view with a wall underneath, which is 200 millimeter thick wall underneath with a floor on top. You can see a load in 4 kilonewton meters this direction, 3 kilonewton meters in the other. We just want 25 kilonewtons. You got both sections, so you can see here you got a floor and a wall, and you can see this section in both directions. If you went discrete instead, so you can see a 1 meter strip essentially. If you went discrete, what would happen is you'd have an edge distance here that you'd need to check as well, and that'd be one of the inputs from a connection perspective. Let's just keep it a continuous, and let's start configuring our design. For our floor, we can go our floor panel. Let's spread the love a little bit with one of our friends. Let's just say we've got a red stag panel. 3-layer, 120, let's just make it a bit thicker actually. A 5-layer, 167.5. That's for the first floor member. For the wall member, you can also then change your update. So you can see here the underneath wall as well, and you got both red stag panels here designed with the third, the connection supplier. Next, for your screw supplier, you can choose your different suppliers here. We do have a good selection of suppliers right now, and I think we're going to go with Spax for this screw. And again, you got this little, well, we got this screw here working dynamically, but you can always just, again, learn from the screw families, from the suppliers here, and learn about their whole entire screw range. And one of those things, what we do help with is product availability. So let's just go a partially threaded screw, A2. Let's go 8mm 160. We're still not thick enough. Let's go 240. I'm starting to penetrate the panel as well. You can see shear capacity. Maybe there's not enough embedment on the bottom, if that's the case. Let's just see if we increase that, we'll probably get a bit of extra capacity. All right, so analytical method. You got the SPAX ETA. I might just leave that at the end and just see what happens. For our loading, let's go 0 in X, 25 in Y. And if we go back to our top view, we've got 25 kilonewtons per meter, and that is the diaphragm reaction scenario that we've got. Design capacity is currently to Eurocode. Well, shear, it's failing by quite a bit, which is quite interesting. If we did say go to an ETA, you know, in this instance, we got a lot more improvement from the ETA then from 600% to 200%. So that's a massive difference, right? So it's like always important to just double check. We could look through the screw families here and get I'm sure if Greg's on the call now, he'd be able to intuitively navigate the range of SPACs really quickly to get the thickest panel. But again, we had an 8 mil in that range. We might need to get a thicker. So here we got 8 delta seal, which is an 8 to 12 millimeter, for example. So delta seal, partially threaded, and because of that, we learned that we can go a wider diameter screw, and if that's how we wanted to do it, we could go to like 10 by 200. For example, we're getting much closer. Almost. But in any case, this is maybe unrealistic loads that I'm putting in. But yeah, so you got the ETA, you got the local design code, you got your spacings. Quite interestingly, if you go inclined screws, well, right now we went inclines there, and you can see here it's failing. So if we went a longer screw, maybe we can get an inclined screw to work. We can here, and all of a sudden we've got the capacity working actually better, interestingly enough. So in any case, you can really quickly design, and now we've got plenty of embedments. So you can see here the shear capacity is working, but the geometric is failing here, right? So you can see here the spacing of member 2, and our wall is too thin to accommodate the screws. So I'd imagine, again, I'm just doing a quick version here of it. But in any case, you can quite quickly check what's working. Well, I think intuitively I forget exactly what member 2 is, but anyway, you'd be able to go in detail and get to the design quite quickly to work out what's working. Cool. And then you got your lateral capacity check. So this is all done in detail as well. Hit save. And what I'd recommend doing is watching our end-to-end webinar on lateral stability and connection design of a post and beam building, where we cover screw design in detail. All right, so finally, we're just going to do a quick sneak peek of our floor penetration calculator. So this has been actually in high demand and been something we're pretty excited to get out, to be honest. So with this will be released on Friday. So we've got a floor penetration calculator. Right now, it's probably done in Deluble, to be honest. So Deluble's quite expensive to fire up and quite time-consuming as well. So we're hoping this can be like a really quick, easy way to do it. It's based on the grillage method from ProHolt. So what you're looking at here is a top view of a floor penetration, and you can see an analysis view the assumption it's done. So based on the grillage method, you've got beams in both sides, basically trimming around the penetration, and the secondary direction of the lamella itself is helping there. So for us, you can see in red, that's when it goes to fail. It'll turn to green if it's passing. So we just went a thicker panel. It's passing in terms of strength, but you can see here we're still failing on deflection based on the default inputs. But for us, let's just go say a 3 meter wide panel, 5 meter long span, opening width. You can start configuring it one by one. Width, the location you can change. So again, working dynamically here, might be on the edge of the panel, might be wherever it might be. And you can see everything calculating accordingly. For design methodologies, loading data. So all of this is quite intuitive, I think, for the inputs, which is good. But what might be interesting and fun to play around with is the next part. So deflection data. So you can see here we're failing in deflection. So for the sake of it, let's just get this working. Let's make it a 4 meter span, and we're working at 99% in that instance. For your floor opening, you can see the assumptions here. So based on the grillage method, it gives you the width of the beams that are trimming around the penetration. For your panel properties, you've got the calculations of the stiffness in both directions. So right now, we're on beam 3 and 4. You can see here, based on the extended gamma method, we are using the secondary stiffness of the panels itself. So it's calculating that in detail for the design. And if you change to beam 5 and 6, you've got the primary direction stiffnesses calculated. So that can be done in detail. For loading combinations, you can see here, that's just your standard loading combinations. But next you've got your analysis. So you can see here, beam by beam, if we click beam 3, we've got the analysis here of how it's calculating as well. If you click beam 5 or 6, you'll notice you'll have 2-point loads from beam 3 and 4. So let's click beam 5 and 6, and you can see here, you got the reactions of beam 3 and beam 4, and you can very quickly determine how it's all working together, bending moment, shear force, and deflection as well. Deflection check, and then your design code check. So with everything, it's like done in detail. So you can see side by side, beam 3, 4, 5, and 6. Lamellas based on the loading combinations. You can see what's done in the design as well. So there's quite a complex calculations under the hood, but really intuitive and fun to play around with. And I think these, like very quickly in this red color, understanding what's failing. So beam 5 and 6 failing here and so forth. So you can play around with it really quickly. That said, we're going to now close or come up to questions. So thanks everyone for your time, and happy to take any questions you might have.
Doesn't appear there are any at this point. But feel free, you can take a moment and pop something in if you do have something. But if not, we might be able to wrap it up there, Adam. What do you think? Thanks for the presentation.
Yeah, no, thanks everyone. And as you said, Corey, we'll be at the WCTE, and this webinar will be online on the community forum, and that release will be going out Friday. So if anyone's got any questions, just let us know. If you want to have access to the app, we can give pro trials, right? And give access to some of these calculators.
Yeah. And stay tuned for the next webinar. It hasn't been locked in perfectly yet, but you'll hear about it soon. So stay tuned for that one, and we hope to see you all there.
All right. Have a good day, everyone, and thank you so much for joining.
Bye, everyone.